Okay, let's solve LeetCode 15, 3-sum, the sequel to the popular question 2-sum. So before you solve this question, the first thing you should do is make sure that you've solved 2-sum, which is the most popular question on LeetCode, so you've probably solved it or at least seen it before. I also recommend solving 2-sum 2, which is basically 2-sum except the input array is sorted. A lot of people skip this question. I think that's what makes 3-sum a little harder because they don't solve this one first. If you solve 2-sum and 2-sum 2, this question 3-sum is pretty straightforward in my opinion. But okay, let's get into the question. So we're given an input array of n integers as per usual. This array though can have duplicates as we can see in the example, right? 2 -1s in this case. Now what we want to do is find 3 numbers of this array, so A, B, and C, and we want them to sum to 0. So in the example, there were 2 elements, or 2 triplets that summed to the total 0. Now one problem is that we cannot have duplicates in our solution. So we're going to have to keep that in the back of our minds. So let's just start the most brute force way. We see that we need 3 numbers, so why not just have a triple loop, right? Just get every single combination of 3 numbers. That's probably the first thing you're going to try, right? So let's say our first number is -3. This is our A. So we're going to try each of these numbers for B, right? This could be a B, this could be a B, this could be a B, this could be a B. This last one can't be a B because we need at least one number to come after it so that it's a C. Now, if we did that with our triple loop, we would find that there is one such combination starting with -3 that will sum to 0. If we take 1 as our B and we take 2 as our C value, because then we'll have -3 plus 1 plus 2, that's obviously 0. So to our solution set, we can say, okay, there's a -3, a 1, and a 2. So now when we move, we can consider this as our first element, right? But eventually we'll see that we go through the entire thing and we don't find anything that can be added to 3 that'll give us a sum of 0. We'll do the same for this one, and there isn't anything. Now we get to a -3 again, though, because remember, there are duplicates in this array. So now we're saying again that we're going to put -3 in this first spot. Now this is a recipe for finding duplicates. This is not good. And we'll see in this example that's exactly what's going to happen. There's another, we'll take this as our B, we'll take this as our C. Again, we find -3 plus 1 plus 2 sums to 0. So then we're going to add that again to our result set, right? But that's not what we want. We want to eliminate the duplicates. So the problem was we took -3 as our A value, right? And then we searched the rest of the array for 2 numbers, 1 and 2, that add to 0. But then we went back here, right? And we found the -3 again, and we did the exact same thing. The problem is we don't want to have the same number in this position, in the A position, twice, because then if there are the numbers that come after it, we could potentially find duplicates. The solution to this problem is to sort the input array. Let me show you what I mean. So here you can see that the array is now sorted. Let's cross out our top array, which was unsorted. So now we are going to sort the input array. So now when we're looking for all combinations, if we find -3 first, then that's good. Okay, we'll say -3, then we find these 2 numbers, 1 plus 2, and then we find our solution. Great. Now if we get to -3 again, we'll say, hey, wait a minute, this number was already in this position, right? And we know that because its neighbor, its left neighbor, is the same value. We don't want to put it twice here, because if we do, we'll get the same duplicate. So we're going to tell ourselves that we already computed all combinations that start with a -3, so we don't need to do that anymore. We already visited this one, we're going to skip this one, and then we're going to go here. So that means in this case, we're not going to find any more results in the remaining portion of the array because they're all positive. They're never going to sum to 0. So then in our result, we're only going to have the one triplet, -3, 1, and 2. We eliminated duplicates by not reusing the same element twice. I think it helps to understand a little bit about the statistics of like combinations and permutations to like understand exactly why this eliminates duplicates, but I hope this explanation at least helped a little bit. So now that we know to sort the input array and we know how to eliminate duplicates. Once we find our first number, notice, right? So let's say we have a -3. So then the remaining part of the problem, there's only 2 elements, right? So it basically reduces to 2-sum. And you probably know how to solve 2-sum, right? Obviously, we can put the numbers, let's say that this is our first A, right? So then for the remaining portion, we're basically going to do 2-sum. And you can do that with a hash map or a hash set. But if you've solved the problem 2-sum 2, you know that we don't need to use a hash map. We can use a left and right pointer. So this is our left, and this is our right. And if we find numbers such that left and right added to our -3 sum to 0, then we're going to add them to the solution set. If the sum, though, is too big, for example, if our sum was greater than 0, we want to decrease our sum. Now we can do that by taking our right pointer and shifting it. So our right pointer would be shifted here. Notice how that decreases the sum because the numbers are sorted. So if you've solved 2-sum 2 before, you know exactly why this works, and I encourage you to watch that video if you want a deeper explanation. Now, on the other hand, maybe our sum is too small, our sum is smaller than 0. In that case, we would shift our left pointer. Because the input array is sorted, if we shift our left pointer, we're increasing the sum. Now, there could be duplicates among these left and right values too. For example, if this 1 was a -3 instead, right? In that case, we don't want to reuse the same element twice, even among our left and right values, so we would not use the same, we would shift our pointer once more over here. We don't want to reuse the same value for left and right either, so we don't get any duplicates. Now, in terms of time complexity, remember we are sorting the array, which is big O of n log n, and then we are not doing the brute force with triple loops. That would be n cubed. We are using the fact that this input array is sorted to our advantage. We're using one loop to tell us the first value, and we're using the second loop to basically solve 2-sum. So we're going to have 2 nested loops, and that's going to give us O n squared. So that means obviously the time complexity reduces to just O of n squared. Now the space complexity will depend. So for the implementation I'm showing, it could be big O of 1 or it could be big O of n, because sorting actually does take extra memory in some libraries. So it depends on your implementation of sorting. It could be O of n. Okay, now let's get to the code. So we remember we have to return this result as a list of lists. And remember, the first thing you want to do is sort the input array. Next, we want to use each number in the input array as a possible first value. So I will iterate through the index and the value. And remember, we don't want to reuse the same value first value. So I will iterate through the index and the value. And remember, we don't want to reuse the same value in the same position twice. So if I is greater than 0, meaning this isn't the first value in the input array, and this value a is equal to nums of I minus 1, that means it's the same value as before. That means we want to continue. We don't want to reuse the same value twice. So we're going to continue to the next iteration of the loop. Next, we're going to use our 2-pointer solution for the remaining portion of the array to basically solve 2-sum. So we'll have left and right pointers. Left will initially be I plus 1. Right will be the end of the list, length minus 1. Left and right can't be equal, so we're going to say left is less than right. Now we're going to actually compute the sums. So we'll say our 3-sum is A plus nums of left plus nums of right. So if the sum is too great, remember, If it's greater than 0, which is what we're looking for, then we need to decrease it, in which case we would say our right pointer needs to be decremented. On the other hand, if it's too small, we need to make the sum bigger. If only I could type today. If it's too small, we need to make it bigger, so shift our left pointer to the right. The last case is if this is equal to 0, so of course we have to add it to our result. So to our result, we're going to append all three numbers. So the numbers are a, nums of left, and nums of right. Now, of course, we got to update our pointers, but how do we update it? There's a lot of ways you can do it, but I'm going to show you the way that you can do it with writing the minimal amount of code. So let me just write a comment to show you a little bit. What if we had the two sum basically for these left and right, and we were at -2, -2, so -2, 0, 0, 2, and 2. What if our left pointer was here and our right pointer was here? In that case, we found a solution, let's say, right? Then we'd want to update our left pointer, right? So then our left pointer gets to -2 again. But that's the same one as before. So in that case, we want to update it one more time to get it over here, right? Now in that case, now our sum is going to be too big because we're going to be at 0 plus 2. So that's greater than 0. So then our loop is going to execute saying that this is too big, and we're going to shift the right pointer to the left. But notice how that right value is now the same as it previously was too, but that's okay because our sum is going to evaluate as too big, so our right pointer is going to be shifted again. Notice how each value is only going to have one corresponding value that it can sum equal to the target, which is 0. So we only have to update one pointer, and our two conditions up here will update the other pointer by itself. We don't even have to worry about it. So in this case, we're only going to shift our left pointer. Because we don't want to have the same sum, we're going to have to use a loop. So in this case, if nums of left is equal to nums of left minus 1, that means it's the same value, so we have to keep shifting our pointer. But remember, we don't want our left pointer to ever pass the right pointer, so we're going to add that to the condition. So this is all we needed to do. Now I believe, unless I've made another stupid bug, we should be able to just return our result and pass the problem with the most optimized solution. Okay, I'm praying that this works on the first try. Let's see. We passed the test case, the first test case. They really want you to buy LeetCode Premium. This is taking... Okay, so it did pass. Usually I have some stupid bugs where I mess up a condition, but okay, so we passed it. This is pretty complicated. I'm not going to lie. This is a pretty hard problem to solve if you've only just solved 2-sum. So I really recommend solving 2-sum 2 as well before solving this problem. I might have made it look easy with the amount of code I wrote, but don't let it fool you. Okay, one pointer, and our two conditions up here will update the other pointer by itself. We don't even have to worry about it. So in this case, we're only going to shift our left pointer. Because we don't want to have the same sum, we're going to have to use a loop. So in this case, if nums of left is equal to nums of left minus 1, that means it's the same value, so we have to keep shifting our pointer. But remember, we don't want our left pointer to ever pass the right pointer, so we're going to add that to the condition. But we don't want our left pointer to ever pass a lie. This is a pretty hard problem to solve if you've only just solved 2-sum, so I really recommend solving 2-sum 2 as well before solving this problem. I might have made it look easy with the amount of code I wrote, but don't let it fool you. I really struggled with this problem the first time I was doing it, and you can see here by looking at the evidence a long time ago, well, 10 months ago, I was pretty bad at this as well. So don't get discouraged. If this was helpful though, please leave a like and subscribe, and thank you for watching.